Hello guys, good evening all. Am I audible? Yes. So tell me, where were we in the last class? Yes, or what happened? Acha, I was sick. Yeah, I had fever that day on Monday. So I thought of, taking rest. So yeah, I was leave on that day. Fine now, like it's what it was not, COVID and all. So yeah, I was a bit worried, but better now. Yeah. Maybe some flu or something. Yes, so yeah, right. Yeah, so we had done the second law of thermodynamics, correct? We have discussed about entropy and second law of thermodynamics, we finished. Okay, so next we are going to start Gibbs free energy, which is the last part of thermodynamics, correct? And the second portion of this chapter is left then, which is thermochemistry. So most probably today we'll finish this chapter, okay? Second law of thermodynamics we have not done. Just a second, Ajiti. Let me just check. We have done second law of thermodynamics. I can see the notes. We have done till TdS is equals to du plus PdV, right? Yeah, so that is it. Second law is done over there. Yes, that's it. We have just statement of second law. That is it. Nothing much. And then we have given the combined statement of first law and second law, which is TdS is equals to du plus PdV. So that is it. It's done. Okay, so next you see, just starting this particular topic here, let's just back and just recall a few things. Okay, if you remember, we had discussed spontaneous process, correct? Right? Spontaneous process. And there are two conditions for this. What are those conditions? The conditions is are enthalpy change negative and delta S, the entropy change positive. Means randomness is increasing, yes? This is what we had discussed. If any process is taking place, the process will be spontaneous under two conditions. Either the enthalpy should decrease, means the process would be exothermic, or the entropy should increase, delta S greater than 0. These are two conditions we had discussed, right? So first we'll talk about randomness, and then to find out randomness or to measure randomness, we have got a new thermodynamic term, and that is entropy, and the entire thing about entropy we discussed, right? Now here what we are going to understand, because this is also temperature dependent function, this is also temperature dependent function. We know if temperature increases, entropy increases. So both terms are temperature dependent. So now what we thought, because suppose any process is given, you need to first analyze enthalpy, or you need to analyze entropy, right? in order to understand the spontaneity of that particular process, right? So what we do, instead of analyzing two different terms, now we thought of what? That we'll combine the two terms and will give a new thermodynamic term. Based on that, we can say directly whether the process is spontaneous or not. Okay. So in this way, like this was a thought process. And what we got into this, we got a new thermodynamic term that we call it as Gibbs free energy. Gibbs free energy is represented by G, and it is given to understand or analyze the spontaneity of any process. Like we, instead of analyzing two different terms, delta H and entropy, we will analyze, Gibbs free energy. We have a condition of Gibbs free energy. Like under this condition, the process will be spontaneous. So we will analyze only Gibbs free energy. And if that condition is satisfied, the process is said to be spontaneous. Okay. So what is Gibbs free energy? It is a thermodynamic quantity. It is a thermodynamic quantity, and it is equals to the amount of useful work done. The amount of useful by work done by the system. Keep that in mind. It is by the system. Amount of useful work done by the system is equal to decrease in the value of Gibbs free energy. Gibbs free energy. Right? So this is useful work done. We'll see there are two types of work done. Till now we were discussing about work done only. So when only work done is mentioned, it means it is the pressure volume work done in general, right? If you have a piston cylinder system. But useful work done is non-expansion work done. It is non-expansion work done. Non-expansion, or we also call it as non-PV. You can also understand this by this way. Like, for example, you have, suppose you have an object, suppose I have this pen in my hand, right? If I place this pen from this point to another point, from this room to another room, right? I have to do some work. And this work done equals to decrease in my Gibbs free energy, right? So if you do any work, if you do any work, that work will be done at the cost of your Gibbs free energy. Obviously, there is no pressure volume thing over here. There's no expansion or contraction we have here. One second, guys. Just to Yes. So useful work done is this. It is non-expansion work done. Correct. Where there is no pressure, where there is no volume things in, right? That is useful work done. So Gibbs free energy is equals to the useful work done, magnitude wise, if you see. Okay. So mathematically, you see, it is defined as D is equals to H minus TS. So if you remember, I just said that in order to analyze this and this separately, we'll combine these two with the help of temperature and we'll give a new thermodynamic term, right? And based on that thermodynamic term, we can say the process is spontaneous or not. So how do we combine the two? We combine H and S, enthalpy and entropy, like this. Correct? T is the temperature. If you look at the change in Gibbs free energy, delta G is equals to delta H minus T delta S. Okay, this equation we call it as Gibbs Helmholtz equation. Gibbs Helmholtz equation. Right? We will see what is the condition for delta G for Gibbs free energy for process to be spontaneous. We'll see that condition. Right? But the physical significance of delta G, what I said, it is the decrease, it is a useful work, right? What is the physical significance of Gibbs free energy we have that you see? Physical significance. So like I said, we have two component of work over here, and that is expansion work and we have non-expansion work. Expansion and non-expansion. Okay, non-expansion is nothing but, like I said, is the useful work we have. Useful work. Okay, expansion, the work in which pressure volume term, like P delta V that we calculate, it is the expansion work. Okay, suppose if you rub your hand, right? If you rub your hand, you will feel some heat. That is non-expansion work. Okay, if you place the box from this point to another point, that is non-expansion work. So that kind of work is useful work we have over here. Okay. Remember, I have given you the definition of Gibbs free energy, and there we have work done by the system. Correct? So what I am assuming here, this condition, the condition I am taking, if Q is the heat absorbed by the system, and and W is the work done. W is the work done by the system. Work done by the system. Correct? So if you see, if I write down from first law of thermodynamics, delta U is equals to Q minus W, because we're working by the system, so minus W will write down this way. So basically, Q is equals to what? Delta U plus work done. Now, further if I write down, because work done has two components, delta U plus we have work done expansion plus work done non-expansion. Okay, copy down this. I'll go to the next slide. Two component of work we have, expansion and non-expansion. Okay, so next time you see, if I write down this expansion work, so that would be Q is equals to delta U, and expansion work we can write P delta V. So work done by the system, I have taken the sign convention earlier also, if you see, that's why I've written Q is equals to U plus W, right? So here I have taken P delta V, right? Minus W I have taken on the top. Plus this I'll write down with this, and this would be non-expansion work. Non-expansion, right? What is this term? Could you tell me? This would be the enthalpy change, delta H. Okay. And this Q we can write Q is equals to T delta S, because entropy change formula is what? It's Q by T. So Q is T delta S, isn't it? So what we can write here, you see, T delta S equals to delta H plus work done non-expansion. So work done non-expansion equals to minus of delta H minus T delta S. This is nothing but the change in Gibbs free energy. So further we can write this as the non-expansion work done or useful work is equals to minus delta G. So if you write down this in this expression in words, what you will write? The useful work done by the system or non-expansion work done by the system is equals to the decrease in Gibbs free energy of the system. isn't it? Okay. So decrease in Gibbs free energy is the measurement of useful or non-expansion work done by the system. Write down this point. This minus sign means Gibbs free energy is decreasing. So we'll write down here decrease in Gibbs free energy equals to useful work done by the system always. Clear? This is the physical significance of Gibbs free energy. Clear? Done? Okay. Next, write down standard free energy change. Standard free energy change. See, standard free energy change is represented by delta G naught. This dot, which is written over here, this dot means standard it is. The condition is a standard state we have. Okay. What is the standard state, standard condition? Standard condition is we have 1 atmospheric pressure, and 298 Kelvin. Okay, 298 Kelvin and 1 atmospheric pressure. Write down, it is the free energy change at standard condition in which the reactants and products are also in their standard state. We'll talk about it. What is the standard state of different molecules, atoms? Okay, later in thermochemistry. Here it is not that useful. Just you need to know that the atoms must be there in standard state. The reactants or products that we have. So at standard state, the free energy change will write like this. Every term will be at the standard condition. So delta G naught means free energy change at standard state. Standard free energy change equals to the enthalpy change at standard state minus the entropy change at standard state. This is the relation we have. Okay, at standard state. Copy this down. What is this? So this is not. No, it's not isothermal process. You are, Anusha, you are talking about this for isothermal because temperature we have taken constant over there, right? Yeah, no, it's not like that. See, the thing is, any process generally we are talking about in reactions over here, right? Because in chemistry, mostly we'll deal with all these things for with respect to a chemical reaction, correct? So in the chemical reaction, what happens? Any chemical reaction takes place at constant pressure and temperature. So whatever the reaction we have, that must we have at a given temperature. Hence, we'll take this temperature out over here. Condition, we don't have such condition that it is for isothermal process. Okay. Yeah. So this is the standard state we have. Now we have a relation here. This relation you have to memorize, but a little bit you should know about it. You should know about equilibrium constant. You know what is equilibrium constant? Tell me. See, I'll tell you a little bit of about this equilibrium constant, but we'll discuss this again in detail in chemical equilibrium. Yeah, right. So a little bit we'll discuss about it. Usually this chapter thermodynamics, I teach this chapter after finishing equilibrium because of this thing only, right? But since they have taken this chapter in the school early, so because of the school thing, I have taken this chapter also before equilibrium. But usually we used to teach this chapter after finishing equilibrium because of this thing only. Here you don't understand about equilibrium. So let me just discuss few things about this equilibrium constant, just expression you should know, and then we'll come back again to this point. Okay. See, first of all, equilibrium constant is represented by Kc is equilibrium constant. You can also write simply K or Kp also you can write. Okay, K, Kc, Kp, anything you can write. Okay. If you have a reversible reaction, it is defined for a reversible reaction. If you have a reversible reaction, A gives B. Reversible means forward, backward, both the reaction may proceed. So we can always calculate the ratio of the product concentration. This square bracket means the concentration. Concentration of what? Product. Concentration of product by concentration of reactant. We can always calculate this. The moment reaction starts, we can start calculating the concentration of reactant, whatever it is. Right? Because when the reaction starts, A starts converting into B, so we'll get some amount of B. So any point, you take the concentration of B and concentration of A, and we can find out this ratio. This ratio, it as Q. That is reaction quotient. reaction quotient. Right? Q is what? Is reaction quotient. Copy this down. I'll go to the next slide. Okay. Now, since A is converting into B, so obviously we can also write this as concentration of the product, which is B, divided by the concentration of reactant, which is A, at any point of time. Now, when you find out this ratio of product and reactant at time T is equals to T equilibrium. When at equilibrium constant time, you'll find out the ratio, then this ratio is said to be Kc, which is the equilibrium constant. Did you get my point? How many of you understood this? Tell me. Ratio of product by and reactant at equilibrium is called equilibrium constant. If you find out the ratio of product and reactant at any point other than equilibrium. So here, this is T does not equal to T equilibrium. But why means what? Or ratio of the concentration of product and concentration of reactant. Yeah, or just 1 second, I'm coming to your question. Kshitiz got it? So either we take concentration of reactant and product, or we can also take pressure if the gaseous phase reaction is there. So when you take the concentration of reactant divided by the concentration of product, that ratio is said reaction quotient. Understood? So it is understood. So just you understand like this. In detail, we'll discuss this in chemical equilibrium, which is the next chapter we have. Okay. The equilibrium chapter is all about this equilibrium constant only. So we'll discuss that. But here just you need to keep in mind, for any reversible reaction, at any point of time, you take the concentration of reactant, take the ratio of both, you will get reaction quotient. If the gaseous phase reaction is there, take the pressure of product, the pressure of reactant, find out the ratio, that will be again the reaction quotient. Okay. Now, equilibrium condition isn't a specific condition, right? It has a specific properties also. Right? It's not like, for any reaction, equilibrium condition is very important. Right? So at equilibrium condition, to define whether the equilibrium condition is maintained or not, for that we have defined a specific term for this ratio, and that specific term is equilibrium constant. Okay, so Q is nothing but Kc at equilibrium, you can say. If equilibrium is not maintained, Q does not equal to Kc. Right. So sometimes what happens, if obviously we'll see this in a next chapter, but why we have defined this term in order to understand the equilibrium condition is maintained or not. So at equilibrium, what we can write? We can write Q is equals to Kc. Reaction quotient is nothing but equilibrium. No, K, we can say K is equals to at equilibrium. It's not like that, Anusha. Value of K, we are not bothering about it now. Okay, what should be the value of K? It could be anything, we don't know about it, right? But the value of K will be constant. It depends only upon temperature. That again we are not bothering about. Okay, all these things we'll discuss in chemical equilibrium. So K value could be anything. Okay, when equilibrium is not maintained, if equilibrium is not achieved, then Q does not equal to Kc. You need to just keep this in mind, nothing much. The expression is what? Concentration of product by concentration of reactant. This is the only thing which is required for this chapter. Other things we'll discuss in chemical equilibrium. Okay. So what happens, you will see this question arrow that some values will be given of reactant and product. You need to find out whether the equilibrium is maintained or not. So what is the condition of equilibrium? We'll find out this Q and Kc. There will be data. If this condition is coming out to be, it means equilibrium is maintained. That's how the specific term is given. Yes? Correct. Go ahead, guys. Tell me Y or N you can type. Yeah. Correct. So what is the relation of delta G and equilibrium constant or reaction quotient? The relation is, this again you have to memorize. This relation is delta G is equals to delta G naught plus RT ln Q. What is Q? You know now. Q is what? Q is reaction concentration of product by concentration of reactant. Okay. So if you write down the equilibrium condition at equilibrium, delta G equals to 0. This is the condition of equilibrium. We'll see this also after some time. And becomes Kc at equilibrium. So these two conditions will substitute here. We'll get the expression. Delta G naught is equals to minus RT ln Kc. This is the expression we have. You know how to convert ln into log? You can write down this as delta G naught is equals to minus 2.303 RT log Kc. Or in terms of, if you want to write down, delta G is equals to minus RT ln Kc. So from this, we will find out Kc equals to e to the r minus delta naught by this delta G naught. Copy down this. How did we get this expression? That is not the concern. You just keep this expression as it is in mind. We'll discuss this later in other chapters. We'll see. Next chapter, probably we'll see. But this equation you must keep in mind at equilibrium condition. Now, if you draw the graph of this relation here, you see it is a logarithmic graph we have. So obviously the graph will be like this. So this one, y-axis is the what is the reaction code Q, and this side we have delta G naught, x-axis delta G naught. This is the logarithmic graph. The graph goes like this. Okay, logarithmic graph goes like this. At some point, definitely the value of delta G is 0. That point is suppose this we have. At this point, suppose that is 0. And if this is 0, you see here, if this value is 0, right, then this means what? The equilibrium is corresponding value of Kc is what? Delta G naught is 0. Kc value is what? This value is Kc. And this Kc value is 1 if delta G naught is 0, isn't it? Write down this way. So when delta G naught is 0, you substitute here. Log value is 1 here. And since it is 0, it is nothing but the only 1 I'll write down. Wait. Yeah, that's fine. Okay. Now, towards the left of this point, we have negative delta G naught, and towards the right, we have positive delta G naught. So whenever delta G is positive, you see, whenever delta G naught is positive, means it is towards the right of it. The value of Kc is what? Here also I'll write down K only. The value of equilibrium constant K is what? If it is positive, the value K is what? Is less than 1. If it is negative, less than 0, you see, draw the graph. The value of K is greater than 1. Greater than 1. And when delta G is 0, the value of K is equals to 1, which is the condition. No doubt? Copied? Okay. Now, the purpose or the objective to define Gibbs free energy is to find out the condition of spontaneity. That was the whole purpose. If you go back and see, I discussed that enthalpy and entropy was the two conditions. So they combined the two terms and they have given the new term, thermodynamic term, that is Gibbs free energy, in order to understand the spontaneity of any process. So the whole purpose is to understand the spontaneity of the given process. Correct. So what is the condition of spontaneity we have? Okay, heading right down, all of you. Condition of spontaneity. We know all this fact that delta S total for spontaneous process is greater than 0. This we know already. But this is the condition with respect to entropy only we have. Right? This is the condition with respect to entropy. What is the condition with respect to delta G that we are trying to understand? So you see here, what I am assuming, you see, I am assuming since any reaction takes place at constant temperature and pressure, so we are, first of all, we are assuming constant temperature and pressure. So at this condition, we assume that Q amount of heat given by the system to the surroundings. To the surroundings. And in this process, obviously some amount of work must be done. Okay. Heat is given by the system to the surrounding. System is giving heat. So its entropy is decreasing. And we can say that the amount of heat is given mathematically, we can write minus Q of system, isn't it? Right? So minus Q of system equals to what we can write? The heat is gained by the surroundings. This is the relation we have magnitude wise. Heat is given by the system equals to heat is gained by the surroundings. Okay. Since we have constant pressure over here, so this Q of the system, we know the heat content of the system at constant pressure is nothing but the enthalpy. So we can write this delta H of the system, negative we have here, so a negative sign we have here. Did you understand this relation? Yes, tell me. Parvati, you got it? Parvati, Anusha, Aditi. These three names I can see here. Yes, okay. Anusha is there? Ansh, Ansh, respond Ansh. Where is Arya? Almost we are done. More minutes, like or 10-15 minutes more. Yeah, okay. So all of you understood this relation we have. Now, if I write down here delta S of surroundings is equals to what we can write? Plus Q of the surrounding divided by T. And this plus Q of surrounding equals minus delta H of the system. So can we write this equals to minus of delta H of the system divided by T, which further it becomes delta S of surrounding equals to minus delta H system by T. Now, the total entropy change expression we have delta S total is equals to delta S sim plus delta S surrounding. Delta S system, you let it be as it is. And delta S surroundings, we can write delta H of the system divided by T. With this expression, this equals to this, so I have written it over here. Clear? Yeah. Now, just we need to solve this, simplify it. And left side we have delta S total. Right hand side, if you see, it becomes minus of delta H of the system minus T delta S of the system divided by T. So we can have T delta S total equals to, what is this term? Could you tell me? Delta H system minus T delta S system. This is delta G of the system, right? So delta G of system is what? Minus of T delta S total. And we know for a spontaneous process, delta S total is what? Greater than 0, and hence T delta S is negative. So the point I want to understand here, this is the relation we got. In this, we'll apply some condition and we'll understand the relation here. So see, so first of all, for spontaneous process, Acha, 1 second, I'll go. Yeah. Okay. So for spontaneous process, we know the condition, that is delta S total is greater than 0. Means this term is positive. This is positive, so delta H system is what? Delta G system is always negative. For spontaneous process, the condition we have. For any reaction, delta G, if you find out to be negative, it is a spontaneous process. So rather than analyzing enthalpy and entropy with two terms, we'll just analyze delta G. If it is negative, spontaneous. If it is positive, then non-spontaneous. Right? For non-spontaneous process, the last one is at equilibrium. We know delta S total equals to 0. When delta S total is 0, delta T of the system also equals to 0 at equilibrium. Copied? Okay. Now the last part of this chapter we have, that is the role of temperature in spontaneity. So we have this delta G is equals to delta H minus T delta S. We have this relation. Now, we are having here two different conditions. The first condition we have means the process could be exothermic and it could be endothermic also. So I'm assuming exothermic process, and we know for delta H is negative always. So first we are considering exothermic and then endothermic, that is it. Okay. So look at the expression of Gibbs. What we need to find out? We need to find out the spontaneity, right? For spontaneity, what is the condition of delta G? Delta G must be what? For a spontaneous process, delta G must be negative, right? So we need to keep this delta G negative here. So what is the condition you see? Delta H is already negative because we have assumed exothermic it is negative, right? Depending upon T delta S, if it is negative or positive, we can easily understand this delta G is negative or positive. So two possibility also we have here. If T delta S is positive, if T delta S is positive, means this term is positive. We already have a negative sign before. Delta H is already negative. Then delta G would be negative. Yes or no? Tell me. Delta G is negative for all temperature. Whatever the temperature you put, it is negative. Right? Negative temperature, obviously, it's not like minus 10 degrees Celsius you put. Right? It is negative, and hence the process is said to be spontaneous at all temperature. Spontaneous at all temperature. So for exothermic process, if T delta, if T is positive, the process is spontaneous at all process. Another condition is if T delta S is negative, if T delta S is negative, then for delta G to be negative, what is the condition? The condition is the magnitude of delta H must be greater than magnitude of T delta S, isn't it? Can we say this condition? For delta G to be negative? Are you getting it? Tell me. Yes, then only delta G would be negative. Okay. This condition can be achieved by, because we need to decrease this term, no? Achieved by decreasing temperature. So what we can say, for exothermic process, if T delta S is negative, then the process will be spontaneous at low temperature. Write down this. Exothermic process, for exothermic process, if T delta S is negative, if T delta S is negative, then the process will be spontaneous at low temperature. Yeah. For exothermic process, if T delta S is negative, if T delta S is negative, then the process will be spontaneous at low temperature. Done? Okay. Now, The second condition we have, if the process is endothermic, delta H is greater than 0, is greater than 0. So again, you see the relation here. This positive, delta S, we need to see this, right? So if T delta S is negative, what does this mean? If T delta S is negative, then this is negative, 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 positive. It means delta G is positive always, right? It will never be negative, and the process will be non-spontaneous. It will be a spontaneous process in this condition. If again the last one is if T delta S is positive, then the condition for spontaneity for delta G to be negative, right? The condition is what? The magnitude of T delta S should be more than the magnitude of delta H, and this condition can be achieved by increasing temperature. Tell me, any doubt in this? Okay. No doubt, tell me. Right. So this is it for this particular thing, right? Thermodynamics, we are done. It's over. Thermochemistry, the second part which is left. We'll start that also, but few before that, we'll discuss few questions on this. All three questions you try. Done. Okay, 78. All the three questions try, Oro, then we'll start discussing. Okay. All the three questions you try, and then we'll start discussing it. All of you. Done? Okay, see, first of all, question number 78. Combustion reaction, it's a factual thing. Combustion reaction is always exothermic. Okay. So whenever wood substance burns in presence of air, there will be heat evolves. Right. So combustion is always exothermic process. So delta H is negative. So wherever we have positive value, eliminate. Okay. Delta S is already positive given in both options. So there's no point of, concluding what would be delta S for this. So let's go directly to delta G. Delta G what? Delta G, we know combustion reaction, any example if you see, it just requires a proper initiation and then it burns on its own, right? So combustion reaction is spontaneous as well. Obviously, delta G is negative, right? So delta H negative, delta G negative, we have only one option. That is option C. Okay. Question number 79. For the reaction, this delta U is given, delta S is given. We need to find out whether it's spontaneous or not. So for spontaneous, the condition is what for spontaneity? Delta G naught must be less than 0. This is what we need to find out. If it is at 0, then we'll be at equilibrium. Delta G we need to find out. Correct. So you see here, what is the formula of delta U? Okay, so delta H is equals to delta U plus delta NGRT, or at standard state. So this, why we have to calculate delta H? Because we know delta G we need to find out. It is equals to delta H naught minus T delta S naught. This is already given in the question, right? Delta S naught is given. We need to find out delta H naught. So delta U naught is equals to minus 10. It's kilojoule here, right? It is joule, right? You must have to notice all these things. Unit is joule. Here it is kilojoule. So what we'll write here? We'll write 10 into 10 to the power 3 joule delta U plus. What is delta Ng? 2 minus 2 minus 1, that is minus 1. R value must be in joule, so 8.314. Temperature is 300. What is this expression? Could you tell me? Tell me the value of delta H naught here. What is the value of delta H naught? Tell me. Minus 12494.2. Is it? So this is minus 12494.2. Okay. Which further we can write minus 12.49 kilojoule approximately, right? Okay. So now you have this delta H naught, substitute this here in kilojoule, minus 12.49, temperature is 300, and delta S over here is given minus 45. So minus 45 into 10 to the power minus 3. Tell me this value, whether you are getting negative or positive. That is what you need to identify, because spontaneity we need to judge. If it is negative, then it's spontaneous. If it is 0, then equilibrium. No, it is given in the question. You see, Anusha, it's given 300 Kelvin, right? Delta S is given at 300 Kelvin. Yeah. So what is this value, negative or positive? So it will be 0.3 into 2. Sorry, 0.3 into 45. Acha. Are we getting this minus 12.49 And this would be plus of 13 point something, is it? Right? So plus of 13 point something, so 5 I'll take. Obviously, this value is coming out to be greater than 0. So when delta G naught is greater than 0, we are getting. So what is the meaning of this? It is B, non-spontaneous. Question number 80. Reversible reaction at temperature T, which of the following is correct? Reversible reaction we have, so we'll assume the equilibrium condition, right? And at equilibrium, delta G would be 0. And when delta G is 0, T is equals to delta H by delta S. So option C is correct here. Clear? Eighty-two, 83, 84, 85. Finish all four and then you can post your answer. Once again, I'll go back. Done. Okay, done. Yeah. Okay. So the enthalpy of vaporization is given. Question number 82, you see. The entropy delta S Hello, can you hear me? Yeah, guys, am I audible? Yeah, actually, sorry, I lost the connection. Some power interruption. Yeah, okay, fine. So this, so you see here that where the enthalpy is given in kilojoule and options are in joule. So we'll just convert this. So 40.63 into 10 to the power 3 joule per mole divided by temperature must be in Kelvin. So 373. What is this value you are getting? All these kind of questions, no, units are very important, must take care of that. So answer here will be 108.9 approximately. So option B is correct, I guess. Yeah. So it is approximately 109, 108.9 joule per mole Kelvin. Option B is correct for this one. Okay. Now, the next question you see, 83. The spontaneous process at all condition of temperature, which of the following is correct? Spontaneous process of delta S must be, negative, right? Delta S must be negative. So this A and B option we can eliminate easily. And at all temperature, it is the first case that we discussed, no? Because how do you proceed in this particular question? You'll write down the expression of delta G is equals to delta H minus T delta S. So at all temperature it is negative. This is negative. This is already negative, exothermic. So for this temperature here, if this enthalpy is negative over here, then for whatever the value of temperature you put, delta G is definitely negative. Means delta H must be negative. It is possible when the process is exothermic. Answer is option D, isn't it? Yeah. Yes, so S is positive. No, that's what. This is positive. Question is what? Spontaneous. Acha, okay, I make my. I thought it is delta G. Yes, yes, yes. That's right. That's right. My bad, guys. I thought delta G is written. Okay, no problem. So spontaneous delta S must be positive. So negative wala option we can eliminate, right? This we can eliminate. And delta H is negative. So we'll have this option B. Yeah, it's B. I thought delta G, my bad. Okay. So this is the answer we have. A spontaneous process, which of the following is correct? Delta S total is positive. Have done this already. Option C is right. For reversible isothermal expansion of an ideal gas, tell me the answer 85. Reversible isothermal expansion. Right? Reversible isothermal expansion, the temperature of system and surrounding must be same, right? So the entropy of system if it decreases, then entropy of surroundings will increase by the same value. So their magnitude would be same, but the sign is opposite, right? So if delta S system is positive, delta S surrounding is negative. So option B is the answer we have here. Tell me, any doubt you have in this? See, all these conditions we have discussed already in the theory part, right? That's what I said, in the beginning, that here in this chapter, we have various conditions. And that conditions you need to keep in mind, that what conditions, how do we approach, right? So you see all these things we have discussed already. So you'll get questions like this in this chapter that you need to solve. I'll share the assignment also on this. Okay. So we are moving next to the, Acha, 1 second. No, like one thing also we'll see. Okay, these three questions you see. Oh, 1 second, 1 second. Preparation of benzene is this. Oh, let it be. This we haven't done yet. Few questions we haven't done yet. Let it be. So next we are going to start thermochemistry.